Graphing Quadratics Day 2. Today's essential question is, how does c affect the graph of f of x is equal to ax squared plus c? So in the exploration that you guys completed today, you noticed that when c was greater than 0, our graph shifted up, and when c was less than 0, our graph was a vertical translation down. The vertex of the graph of f of x is equal to ax squared plus c is 0, c, because our axis of symmetry is remaining the same at x is equal to 0. When we talk about x-intercepts, the value of x when it is the value of x when y equals 0. A 0 of a function is another name of an x-intercept. So x-intercepts and zeros are the same thing, they just have two different names. A quadratic function may have how many zeros? A quadratic function may have 1, 0, if its vertex is on the x-axis. It may have 2 zeros if it crosses the x-axis in 2 places, or it may have 0 zeros. Your quadratic function, there is a possibility that it will not cross the x-axis at all. What do you notice when you use the x-intercepts and plug these x values into the equation? So if we were to plug positive 1 or negative 1 into our equation, negative 1 squared minus a negative 1 minus 2, 1 plus 1 minus 2 is equal to 0. So the y-coordinate equals 0 when you plug an x-intercept in. Y-intercepts is the y-coordinate of the point where the graph intersects the y-axis. The x-coordinate of this point is always 0. So for a quadratic function written in the form y equals ax squared plus bx plus c, if x equals 0, y is equal to your constant or your c. The y-intercept of a quadratic function is always your constant or your c, and we write it 0, c. You can see in these examples that our c or our constant is negative 2, and it's touching or crossing our y-axis at negative 2. Our c or our constant is positive 4. Our y-intercept is positive 4. Our c or our constant is negative 3, and again, it is crossing our y-axis at negative 3. Example 1, graph the function and then compare the graph to the graph of f of x is equal to x squared. So remember, this is our parent function, and we're going to compare these graphs to our parent function. When we graph, we can use a t-chart. The most common values, as long as there's not a fraction for the coefficient or our a, is negative 2, negative 1, 0, 1, and 2. When you evaluate a function, you're plugging x into your rule and stating what your outcome is. In this case, we have g of x. When we plug negative 2 into our function, negative 2 squared plus 5 is equal to 9. When we plug negative 1 in, negative 1 squared plus 5 is a positive 6. 0 squared plus 5 is 5. 1 squared plus 5 is 6. And 2 squared plus 5 is 9. We then want to plot these ordered pairs on our coordinate plane. So we have an ordered pair at negative 2, 9. Negative 1, 6, 0, 5, 1, 6, and 2, 9. You then want to connect your dots and make a nice curve. Do we have any zeros? What are the x-intercepts of our graph? Well, our quadratic does not cross our x-axis, so we say there are no real zeros. So how does our graph compare to our parent function? What happened? you can see that our graph moved up 5 spots. So you can describe that as move up 5 units. Let's look at another example. The second example says h of x is equal to negative 1/4 x squared plus 4. So let's pick some values for our t-chart. Please recognize that we are working with a fraction that has a 4 in the denominator. So if we choose numbers that are divisible by 4, it will cause less of a headache for us. Now let's evaluate this function by plugging each of these x values in and determining what our h of x or our y equals. When we input negative 8 into our function, negative 1/4, put your negative 8 in parentheses, square it, and then add 4. Negative 8 squared is 64, negative 8 times negative 8. 64 times negative 1/4. So 64 divided by 4 is 16, and then when you add 4 to that, you get 20. When you do negative 4 squared, you get 16. Divide that by 4, or negative 4, so you get negative 4. This should be a negative 20. Let's redo negative 8. So if we have negative 8 squared, we get 64. 64 times negative 1/4, which is the same as dividing by negative 4, you get negative 16 plus 4 is negative 12. When we plug 0 in, 0 squared is 0. 0 times negative 1/4 is 0, plus 4 is 4. When we plug 4 in, 4 squared is 16. 16 times negative 1/4 is negative 4, plus 4 is 0. 8 squared is 64. 64 times negative 1/4 is negative 16, plus 4 is negative 12. So when we look at our table, we notice we have made a mistake somewhere because our answers are not matching up. So after our vertex, we should have the same numbers on either side. So let's try evaluating negative 4 again. Negative 4 squared is positive 16. 16 times negative 1/4 is negative 4. Negative 4 plus 4 is 0. So a quick and easy way to check to make sure your points are correct is to make sure that your values are repeating on the left and the right. Then we can graph these points. So we have a point at 0, 4. We have a point at negative 4, 0, 4, 0, and negative 8, negative 12. And I notice that this goes off my graph. So you can, because it's not too terribly far, you can do a quick point at the end. Can we state what our zeros are? It crosses my x-axis at negative 4, 0 and 4, 0. Crossed in two places, we have 2 zeros. When we compare this graph to our parent function, we noticed that there was a vertical shrink because our A value was between 0 and 1. Our graph got wider. And we also know that because our A was negative, it reflected over the x-axis. We also can see that it moved up 4 units. So let's look at example 2. Example 2 says, let f of x equals negative 0.5 x squared plus 2, and g of x is equal to f of x minus 7. Part A says, describe the transformation from the graph of f to the graph of g. Then graph f and g on the same coordinate plane. So when we evaluate these functions, to evaluate f of x, we are going to plug our x into our f of x function and see what these are. So the first point we're going to plug in is negative 4. So if you put negative 0.5 times negative 4 squared plus 2, we get the value of negative 6. When we evaluate negative 2, we're going to plug negative 2 in for our x, so negative 0.5 times negative 2 squared plus 2 will give us the value of 0. When we plug 0 in, negative 0.5 times 0 squared is 0 plus 2, gives us a positive 2. When we plug 2 in, negative 0.5 times 2 squared plus 2 gives us a value of 0. And when we plug 4 in, negative 0.5 times 4 squared plus 2 gives us a value of negative 6. We then want to plug g of x, the rule says f of x minus 7. So we're going to take these values, f of x, and we're going to subtract 7 from each of them. So negative 6 minus 7 more gives us a negative 13. 0 minus 7 gives us a negative 7. 2 minus 7 gives us a negative 5. 0 minus 7 is a negative 7, and negative 6 minus 7 is a negative 13. We then can plot these points on a coordinate plane. When we graph these functions, you can see that the black function is f of x and the blue function is g of x. We then can make a comparison to describe what's happening. What happened when we went from the f of x, or the black function, to the blue function? Please notice that on your graph they count by 2's. So we can say that g of x shifted 7 units down from f of x. Then they said write an equation that represents g in terms of x. So what we want to do is we want to start with our g of x function, which we know from above is f of x minus 7. Do we know what the f of x function is? Yeah. So we're going to replace our f of x with negative 0.5 x squared plus 2 minus 7. We then want to combine our like terms. So g of x, the g function in terms of x, is negative 0.5 x squared minus 5. So you just are plugging one function into another so that we have everything in terms of x. Example number 3 says the function f of t is equal to negative 16t squared plus s sub o. S sub o, please remember, is just one term. This represents the approximate height in feet of a falling object, t seconds, after it is dropped from an initial height, which is represented by S sub O. An egg is dropped from a height of 64 feet. So we know that the initial height, or the S sub O, is 64. Question A says, after how many seconds does the egg hit the ground? So we want to start with 0 seconds for our time. And at 0 seconds, it's going to be the initial height that it's falling from. So we know from our problem that that is 64. We then just want to count by seconds, 1, 2, and evaluate our function for the given time. So when we plug 1 into our above equation, negative 16 times 1 squared plus 64, and we simplify using our order of operations, we get 48. When we evaluate for 2, or find out the height of our egg after 2 seconds, we plug 2 in for our t, because that's the time. We follow our order of operations and do 2 squared, multiply it by negative 16, add 64, and we get 0. So the first thing we did was we made a table of values. Now we want to sketch a graph for that table of values. So please make sure that you label your x-axis as time. You can see our t down here represents our time. You can see our y represents our height in feet. So we know that we have 64 and 0, and we have to make sure that our graph reaches 64 and it also ends at 0. So you can see I plotted these points. So I have an ordered pair at 0, 64. I have an ordered pair at 1, 48. And I have an ordered pair at 2, 0. So after how many seconds does the egg hit the ground? So we can say that when we hit t is equal to 2 seconds, f of t, or the height of our egg, is at 0. So we can say that the egg hits the ground. Make sure you write a sentence after 2 seconds. They then go on to tell us, suppose the initial height is adjusted by k feet. How will this affect part A? So we want to, if k is greater than 0, what happens? So if we increase our value of k, what's going to happen for the amount of time it will take our egg to hit the ground? If k is less than 0, so we decrease our height, how will that affect our time? So if we increase our height, it should take longer for our egg to hit the ground. So we will say we'll take more than 2 seconds. If we decrease our value of k, or the initial height, it will take less than 2 seconds. You now can complete your online practice 8.2, or if you're using the book, page 429, numbers 1 through 3, 6, 8, 10, 11, 16, 18, 20, 22, 27, 29, and 30.